Somewhere above you tonight, there is a patch of sky no larger than a grain of sand held at arm's length. If you looked at it with your own eyes, you would see nothing. Not a star, not a smudge of light, just black. In 1995, a telescope was pointed at that nothing for 10 straight days. What came back was not nothing. It was thousands of galaxies layered behind each other in a single sliver of dark, each one holding billions of stars of its own. A piece of sky small enough to blink past, and inside it, more galaxies than most of us will ever hold a number for. That image asked the question astronomy still has not fully answered. Not how far the universe reaches, not how old it is, something quieter and somehow harder. How many galaxies actually exist within it? We are going to sit with that question tonight. Not rush it, not resolve it too quickly. Just follow it, patiently, the way it deserves. Get comfortable, wherever you are. Let's begin. There is something almost embarrassing about this question, if you think about it for more than a moment. Humanity has weighed black holes. We have listened to the collision of two dead stars from over 1 billion light-years away, felt through the faint stretching and squeezing of space itself. And yet, how many galaxies actually exist is a question we still cannot answer with a single, confident number. It sounds like it should be simple. You look, you tally, you write down the total. But galaxies are not sheep in a field, and the sky is not a fence you can walk the perimeter of. The sky has no edges to count inward from. It only has depth, and depth is where this question quietly falls apart. For most of human history, the question could not even have been asked, because the idea it depends on did not exist yet. Ancient astronomers across nearly every culture, Babylonian sky watchers, Greek philosophers, medieval Islamic astronomers who built remarkably precise pre-telescope instruments, looked up and saw stars. Just stars, fixed to a single turning sky. There was no second category. No sense that some of those points of light were not stars at all, but entire other assemblies of stars, so distant that billions of individual suns had blurred into one soft smear of light. If you enjoy sitting with a question like this one, the kind that takes its time rather than rushing to an answer, it helps this channel if you let the video keep playing and leave a like on your way past. Nothing more than that. That smear of light was there, though, long before anyone understood it. On a clear night, away from city glow, a faint hazy patch is visible near the constellation Andromeda, if you know where to look. Persian astronomer Abd al-Rahman al-Sufi recorded it in the year 964, describing it in his Book of Fixed Stars as a little cloud. He had no way of knowing that the cloud he sketched by hand was, in fact, a separate galaxy, roughly 1 trillion stars, sitting 2.5 million light-years from the one he stood on. That mistake, in a way, is the whole history of this question in miniature, not carelessness, simply a missing idea, the one that would have let the observation mean what it actually meant. Al-Sufi saw the thing itself, accurately, centuries before anyone had a framework to understand it, and for nearly 1,000 years afterward, almost no one thought to ask what it actually was. The telescope, invented in the early 1600s, should have settled the matter faster than it did. Galileo turned his instrument to the sky in 1609 and found that the Milky Way was not a smear at all, but countless individual stars, too faint and too close together for the naked eye to separate. If the Milky Way was made of stars beyond counting, perhaps the universe itself was larger than anyone had assumed. But even Galileo had no reason to suspect that some of the other faint smudges scattered across the sky were not part of the Milky Way at all. that a handful of them were entire separate versions of it. For the next 2 centuries, catalogs of these smudges grew longer. Astronomers called them nebulae, simply Latin for cloud, a placeholder for something no one could yet explain. Charles Messier, cataloging comets in Paris in the 1770s, kept mistaking these fuzzy patches for the comets he was actually hunting, and in irritation, began listing them separately, just to stop confusing himself. That list, meant only to eliminate distractions, became one of the most cited catalogs in astronomy. Many of its 100+ entries were never clouds or curiosities. They were galaxies. Messier had no way of knowing that. By the middle of the 1800s, telescopes had grown strong enough to resolve some of these smudges into something structured. Lord Rosse, observing from Ireland in 1845, with the largest telescope in the world at the time, one he had built himself, turned it toward one of Messier's catalog entries and saw, for the first time, a spiral, arms curling outward from a bright center, like a whirlpool frozen in light. He had no idea what he was looking at, only that it was clearly not a shapeless cloud of gas. The question had a shape now, even without an answer. Something out there had form, and if it had form, it had to be made of something, though no one could yet say how many somethings, or how far away, or whether Lord Rosse had sketched a small local curiosity or an entire galaxy larger than his own. That uncertainty would not be settled quietly. It would take another 75 years, a heated public debate between 2 respected astronomers and one of the most important measurements in the history of science before anyone could say, with real confidence, what those spiral shapes actually were. Before the counting could begin, astronomers first had to answer a far more basic question, one that seems almost too simple to have taken so long. Were those spirals part of our galaxy, or were they entirely separate universes of their own? That basic question, galaxy or not a galaxy, had actually been asked once before, more than a century earlier, by a philosopher who never once looked through a telescope himself. In 1755, Immanuel Kant proposed something quietly radical. He suggested that the faint, elongated nebulae astronomers kept cataloging might not be clouds of gas within our own Milky Way at all. He called them island universes, vast, distant collections of stars, each one a galaxy in its own right, scattered across a universe far larger than anyone had dared to imagine. It was a beautiful guess, built entirely on reasoning rather than observation. Kant had no way to test it. He simply noticed that some nebulae appeared flattened, disc-shaped, oriented at different angles to our line of sight, exactly what you would expect if you were looking at other galaxies from different sides, the way a coin looks like a line from its edge and a circle from above. For well over a century, Kant's island universes remained speculation, elegant but unproven. The instruments simply did not exist to settle it either way, and so the nebulae sat in a strange scientific limbo, catalogued, sketched, admired, but fundamentally unclassified. Were they nearby clouds of gas and dust, small and local, drifting somewhere inside our own galaxy? Or were they, as Kant had guessed, entire other galaxies, so distant that their light had traveled for millions of years just to reach a human eye? By the early 20th century, this unresolved question had become one of the most contentious debates in American astronomy. And in April of 1920, it came to a head in a public forum in front of the National Academy of Sciences in Washington, D.C. 2 respected astronomers, Harlow Shapley and Heber Curtis, were invited to debate the scale of the universe itself. History remembers it now as the Great Debate, though at the time it was simply titled, with academic modesty, The Scale of the Universe. Shapley argued that the Milky Way was enormous, far larger than previously believed, and that it likely contained everything astronomers were observing, including the spiral nebulae. In his view, our galaxy was essentially the entire universe. The spirals were nearby objects, gas clouds or forming star systems, well within the boundaries of our own galactic disk. Curtis argued the opposite. He believed the Milky Way was comparatively modest in size, and that the spiral nebulae were exactly what Kant had proposed a century and a half earlier, separate island universes, each containing billions of stars, sitting at staggering distances beyond our own galaxy's edge. Both men brought real evidence to the stage that day, not just opinion, and the specific evidence is worth pausing on, because it shows how reasonable it was, at the time, to land on either side. A colleague of Shapley's at Mount Wilson, an astronomer named Adriaan van Manen, had spent years comparing photographs of several spiral nebulae taken years apart, and reported detecting measurable rotation. If that rotation was real, and if the nebulae sat as far away as Curtis proposed, their outer edges would have to be moving faster than the speed of light, an impossibility. Van Manen's measurements, offered in good faith by a respected observer, seemed to settle the matter in Shapley's favor. Curtis countered with a different piece of evidence entirely. He pointed to a bright stellar explosion, a nova, observed in Andromeda in 1885, so brilliant it had briefly outshone the entire surrounding nebula. If Andromeda were truly small and nearby, an explosion that bright made sense. If it were a separate galaxy at enormous distance, that single star would have needed to release an almost impossible amount of energy. Curtis guessed there might simply be two distinct classes of stellar explosion, a guess that later turned out to be exactly right, once astronomers identified supernovae as a separate, vastly more energetic phenomenon. What makes the Great Debate worth remembering is not that one side won outright, because in the strictest sense, neither did. Shapley was largely correct about the size of the Milky Way itself, which turned out to be far larger than earlier estimates. Curtis was largely correct about the nature of the spiral nebulae, which turned out to be separate galaxies, just as Kant had guessed. Van Manen's rotation measurements, the evidence that had seemed so decisive in Shapley's favor, were later shown to be mistaken entirely, an honest error introduced by the sheer difficulty of measuring motions that small using early 20th century photographic equipment. Both men were arguing from the best evidence available to them, and both were reasoning carefully from data that, in at least one case, simply turned out to be wrong. The debate did not resolve the question, it sharpened it. That measurement required something very specific, a reliable way to determine distance. Not an estimate, not a rough guess, based on brightness or size, but an actual, trustworthy number. How far away is this nebula, in miles, in light years, in some unit that could be compared directly to the known size of our own galaxy? Without that single number, the debate could continue indefinitely, because brightness alone could not distinguish between a small, dim, nearby object and a large, bright, distant one. A candle held close and a bonfire held far away can look identical from the right vantage point. Astronomers needed something that worked less like a guess and more like a ruler. The tool that would eventually provide that ruler had already been discovered, more than a decade earlier, by a woman working in near-total obscurity at the Harvard College Observatory, cataloging photographic plates for a fraction of what her male colleagues were paid, in a role the observatory itself referred to, without irony, as a computer. Her name was Henrietta Swan Leavitt, and the pattern she noticed in 1908, buried in thousands of photographic measurements of variable stars, would eventually become the single most important tool in the history of distance measurement, the key that would finally let astronomers step outside the argument entirely and simply measure the answer. Henrietta Leavitt's discovery began with something almost tedious in its repetition. Working at the Harvard College Observatory, she was assigned to study a particular class of star called Cepheid variables, stars that brighten and dim in a regular, repeating cycle, like a slow cosmic heartbeat. Working through thousands of photographic plates of the small Magellanic Cloud, she noticed something remarkable buried in the pattern. The brighter a Cepheid variable star actually was, the longer its cycle of brightening and dimming took. Not roughly, not approximately, it followed a precise mathematical relationship, one she published in 1908 and refined further by 1912. This mattered enormously, and the reason takes a moment to sit with. If you know how a star's true brightness relates to how long its cycle takes, you can measure that cycle from any distance, figure out how bright the star actually is, compare that to how bright it appears from Earth, and calculate exactly how far away it must be. A star that looks dim because it is genuinely faint, and a star that looks dim because it is genuinely far away, can finally be told apart. Leavitt had built, without ever intending to, a cosmic measuring tape. Astronomers simply had not yet had anything sitting inside a nebula precise enough to use it on. That changed in the early 1920s, at Mount Wilson Observatory in California, home to the Hooker telescope, a 100-inch mirror that was, at the time, the largest and most powerful telescope on Earth. A young astronomer named Edwin Hubble had been photographing what was then still called the Andromeda Nebula, the same faint smudge Al-Sufi had sketched nearly 1,000 years earlier, the same object at the center of the still unresolved debate between Shapley and Curtis. In October of 1923, examining a photographic plate of Andromeda, Hubble identified a star that appeared to be varying in brightness, a Cepheid. He marked the plate with an excited notation still preserved in the observatory's archives, var, variable. Using Leavitt's relationship between a Cepheid cycle and its true brightness, Hubble calculated the distance to that single star, and by extension, to Andromeda itself. The number he arrived at was staggering for its time, something in the range of 900,000 light-years, later refined by improved calibration to the far larger figure we now accept, roughly 2.5 million light-years. Even that early, imprecise first estimate was enough. The Milky Way, however large Shapley believed it to be, did not stretch anywhere close to that far. Andromeda could not possibly be inside it. Consider what this single measurement actually settled. Not a small dispute, not a minor technical correction. It resolved, in one calculation, a debate that had occupied astronomers for over a century, stretching back to Kant's original guess in 1755. Andromeda was not a nearby cloud of gas. It was an entire other galaxy, comparable in scale to our own, sitting so far away that the light Hubble was examining on that photographic plate had left its source before human civilization had learned to write. Hubble did not keep the discovery to himself. He wrote to Shapley directly, informing him of what he had found, including a light curve of the star as evidence. Shapley, upon opening that letter in his office at Harvard, is reported to have turned to a colleague present in the room and said simply, "Here is the letter that destroyed my universe." It is a remarkable thing to witness, even secondhand, a century later. A scientist recognizing, in the space of reading a single page, that the framework he had spent years defending in public debate had just been quietly, irreversibly overturned by a piece of evidence he had no grounds to dispute. Hubble announced his findings publicly on January 1, 1925, at a meeting of the American Astronomical Society. He did not attend in person. His paper was read aloud on his behalf, a fairly ordinary practice at the time, but there is something fitting about it in hindsight. The announcement that fundamentally reorganized humanity's understanding of the universe's scale, delivered secondhand, in a conference room, to an audience that had no way of knowing they were witnessing the end of one era of astronomy and the beginning of another. Because if Andromeda was a separate galaxy, then the countless other spiral and elliptical nebulae, catalogued over the preceding 2 centuries, almost certainly were too. The Milky Way was not the universe, it was one galaxy, among what might be an enormous number of others, each one an island of stars, floating in a darkness whose true size no one had yet begun to measure. The question this raised was immediate and obvious, and it is the same question that opened this video. If the universe contained more than one galaxy, more than a handful, more than the few dozen bright examples visible through even the best telescopes of the 1920s, then how many actually existed? Hubble himself would spend much of the following decade trying to answer exactly that question, and what he found would reshape astronomy for the second time in less than 10 years, though not by counting galaxies directly, by discovering that they were moving away from us and from each other in a pattern that suggested something no one had previously dared to propose about the universe itself. Before that larger discovery could be absorbed, though, astronomers faced a more immediate and practical problem. If galaxies existed beyond the Milky Way in genuinely large numbers, someone eventually had to try counting them, at least well enough to put a number on paper. Through the 1930s and into the following decades, astronomers did exactly that, using the largest ground-based telescopes available, photographing patches of sky, and tallying every faint smudge that resolved into a probable galaxy rather than a foreground star. The results were, by necessity, rough. Ground-based telescopes, however large their mirrors, share a common limitation that has nothing to do with the skill of the astronomer looking through them. Earth's atmosphere sits between the telescope and the sky, and it is never perfectly still. Warm and cool pockets of air drift and mix continuously, bending starlight in slightly different directions moment to moment. This is the same effect that makes stars appear to twinkle to the naked eye, and while twinkling looks pleasant from a backyard, it is a serious obstacle for precision astronomy. It blurs fine detail. It smears faint light across a slightly larger area than the object actually occupies, making dim, distant galaxies harder to distinguish from noise, and sometimes impossible to detect at all. There was a second limitation, harder to work around than the first. Ground-based telescopes, however carefully positioned, still had to look through the full thickness of Earth's atmosphere, which absorbs and scatters certain wavelengths of light before they ever reach the ground. Some of the faintest, most distant galaxies emit most of their light in wavelengths that never survive the journey through that atmosphere at all. Astronomers were not just looking through a slightly blurry window. They were looking through a window that filtered out some of what they most needed to see. Given these constraints, the counts that emerged from the 1930s through the 1980s varied considerably, depending on the telescope, the location, the wavelength studied, and the assumptions built into each survey's extrapolation method. Estimates during this period generally clustered somewhere in the range of tens of billions to just over 100 billion galaxies within the observable universe, though the uncertainty attached to these numbers was substantial, often unstated outright, and rarely emphasized in the popular science writing of the era. A number would appear in a magazine or a textbook, stripped of its error bars, and take on a confidence in public memory that the original researchers had never actually claimed for it. This is worth sitting with for a moment, because it says something true about how science moves that gets lost when only the final answer survives. Every one of those early estimates was built by honest astronomers doing careful work with the best instruments available to them. None of them were wrong to publish a number. The problem was never the astronomers. The problem was the atmosphere itself, sitting permanently between every ground-based telescope on Earth and the faint, ancient light it was trying to measure. What astronomers actually needed was almost embarrassingly simple to state and almost impossibly difficult to achieve. They needed a telescope above the atmosphere entirely, something in orbit, looking down through nothing but empty space, unaffected by turbulence, unfiltered by absorption, able to gather the faintest photons a distant galaxy could offer without an ocean of shifting air in the way. One astronomer who worked on the Hubble program later summarized the entire problem in a single plain sentence. Trying to do stellar observations from the ground, he said, was like trying to do bird watching from the bottom of a lake. That idea existed in astronomical circles for decades before it became reality, and it has a specific origin worth naming. In September of 1946, a young astrophysicist named Lyman Spitzer, working at that time within a Rand Corporation think tank studying future applications of rocketry, wrote a paper titled "Astronomical Advantages of an Extraterrestrial Observatory." Spitzer was proposing something that, at the time, sounded closer to science fiction than engineering: a large reflecting telescope launched into orbit, positioned permanently above the atmosphere, that had frustrated every ground-based astronomer before him. He wrote this 11 years before the Soviet Union launched the first artificial satellite, and 12 years before NASA itself existed as an agency. Spitzer would go on to spend nearly the entire remainder of his career advocating for the idea through decades of skepticism, budget constraints, and competing priorities, living just long enough to see his proposal become the Hubble Space Telescope, and to spend his final working day at Princeton discussing its early results with colleagues. It would take until 1990, and a launch that very nearly ended in catastrophic failure, before that idea became a working instrument. And it would take 3 more years after that, and a repair mission carried out by astronauts working in the vacuum of space itself, before the instrument could finally do what Spitzer had first described nearly half a century earlier. What that telescope eventually saw, when astronomers finally trusted it enough to point it at what looked like the emptiest patch of sky they could find, would replace every ground-based estimate that had come before it. The telescope was called Hubble, named in honor of the same astronomer whose 1923 measurement of Andromeda had settled the island universe debate 7 decades earlier. It launched aboard the Space Shuttle Discovery in April of 1990, and its early results were, for a painful stretch of time, close to worthless. A flaw in the shape of its primary mirror, ground incorrectly by a fraction of a hair's width, left every image slightly, persistently blurred. The flaw was tiny by any ordinary standard, roughly 1/50th the width of a human hair. But at the scale Hubble was meant to operate, that fraction was enough to undermine the entire mission. It became something of a public embarrassment, a punchline in newspaper cartoons, a costly government telescope that could not quite see straight. That failure was corrected in December of 1993, when astronauts aboard the Space Shuttle Endeavour performed one of the most technically demanding repair missions in the history of spaceflight, installing a corrective optics package during a series of spacewalks in the vacuum above Earth. The fix worked. Hubble's vision sharpened almost immediately, and for the first time, astronomers had an instrument that could see clearly, undisturbed by atmosphere, further and fainter than any telescope before it. By 1995, Hubble had been operating successfully for roughly 2 years, and its director, an astronomer named Robert Williams, faced an unusual decision. As director, Williams controlled a modest allocation of what is called discretionary time, telescope hours set aside for the director's own judgment rather than allocated through the normal competitive process other astronomers use to request observing time. Most directors use this time cautiously, on safe, well-justified projects likely to produce clear, publishable results. Williams proposed something considerably riskier. He wanted to point Hubble at a small, unremarkable patch of sky in the constellation Ursa Major, a region chosen specifically because it appeared to contain almost nothing. No bright stars, no known galaxies, no obvious astronomical interest of any kind. And he wanted to hold the telescope on that empty-looking patch for 10 consecutive days, gathering light continuously, an enormous commitment of an extraordinarily scarce and expensive resource. The proposal was controversial within the astronomical community, and understandably so. 10 days of Hubble time represented a significant fraction of the telescope's total annual observing capacity, and Williams was proposing to spend it on a target selected specifically for its apparent emptiness, with no guarantee whatsoever that anything of scientific value would be found there at all. Some astronomers argued the time would be better spent on known objects of established interest. John Bacall, one of the scientists most closely associated with Hubble's original creation, approached Williams directly, more than once, to argue against the idea, having previously published a paper suggesting the telescope was unlikely to reveal any meaningful new population of faint galaxies at all. Robert Kirshner, an astronomer at the Harvard-Smithsonian Center for Astrophysics, was similarly skeptical at the time, viewing the plan as a poor use of an irreplaceable resource. Others worried openly that the observation would simply confirm what the patch of sky already appeared to be: nothing. Williams made the decision anyway, reasoning that if the deepest, most sensitive telescope humanity had ever built could not find anything interesting in a patch of apparently empty sky, that absence would itself be a meaningful scientific result, worth knowing. He would later describe his own reasoning simply, saying that scientific discovery requires risk, and that he was prepared to resign over the decision if it turned out to be a costly mistake. Between December 18th and December 28th of 1995, Hubble held its position on that single small patch, near the handle of the Big Dipper, roughly 1/24th of the width of the full moon as seen from Earth, gathering starlight in 342 separate exposures, layered together over more than 100 hours of cumulative observing time. What came back did not look like nothing. It did not look like a modest scientific curiosity either. When the exposures were combined and processed, the resulting image contained not the handful of galaxies a cautious astronomer might have hoped for, but approximately 3,000 of them, layered behind one another at wildly different distances, filling what had appeared through every previous instrument to be simply empty, uninteresting darkness. Kirshner, watching the result unfold, would later put his change of mind plainly, saying simply that Williams had been right and that he himself had been wrong. The image would become known as the Hubble Deep Field, and it did not answer the question of how many galaxies exist in the universe. It fundamentally changed the scale of the question itself. To understand what the Hubble Deep Field actually meant, it helps to be precise about just how small that patch of sky really was. The field of view Williams selected covered roughly 1/24th of a millionth of the entire sky, an area so small that if you held a grain of sand at arm's length, it would roughly cover the same patch of darkness the telescope had spent 10 days staring into. Within that single grain of sand sliver of the universe, astronomers counted approximately 3,000 distinct galaxies, most of them so faint and so distant that no previous ground-based telescope had ever detected them at all. The implication of that number is where the real weight of the discovery sits, and it comes down to a piece of reasoning astronomers call extrapolation. If a patch of sky covering 1/24th of a millionth of the total sky contains roughly 3,000 galaxies, and if that patch is genuinely representative of the sky as a whole, then multiplying that density outward across the full sky produces a staggering total. The math is not complicated. It is the assumption underneath the math that carries all the risk. Extrapolation only works if the sample you started with actually resembles the whole. A single grain of sand patch of sky, chosen specifically because it looked empty and unremarkable, had to stand in for the entire dome of the heavens above every point on Earth. Astronomers checked that assumption as carefully as they could. Follow-up deep field observations aimed at entirely different, unrelated patches of sky in different constellations returned strikingly similar galaxy densities. The universe, at this level of resolution, appeared to be remarkably uniform in its distribution of galaxies across large scales, a principle cosmologists had theorized on other grounds for decades, but had never confirmed with this kind of direct visual evidence. When NASA released the image publicly in January of 1996, the accompanying analysis suggested the count of galaxies within the observable universe should be raised from a previous lower estimate of around 10 billion to a new figure closer to 50 billion, a five-fold increase built directly from the deep field's extrapolated density. Even that revision undersold, in a sense, how much uncertainty had existed even before the deep field. Ground-based estimates prior to 1995 had already ranged as widely as 10 billion on the low end to as much as 100 billion on the high end, depending largely on how confidently a given survey believed it had accounted for faint dwarf galaxies. What the deep field actually accomplished was narrower and more rigorous than the popular headlines suggested. It allowed astronomers to raise the confident lower bound of that existing range from 10 billion to 50 billion using the first direct space-based sample deep enough to test the assumption properly. As the astrophysicist Neil deGrasse Tyson later observed, what the coverage should have emphasized was that specific, careful correction rather than presenting 50 billion as some newly discovered final total. In simple terms, what the deep field revealed is that emptiness itself was largely an illusion created by the limits of earlier instruments. Every patch of sky that had ever looked dark and uninteresting through a ground-based telescope was, in fact, full, layered many galaxies deep, simply too faint and too distant for any previous technology to register. The universe had not gotten larger between 1990 and 1995. Humanity's ability to see it had. It is worth pausing on what this number actually represented, because the distinction matters and it is easy to lose. 50 billion galaxies was not a count. No one had counted 50 billion of anything, and no human being ever will, not directly, not one at a time. It was a statistical extrapolation built from a genuine, careful measurement of a very small representative sample, projected mathematically across a much larger area that had not itself been directly observed. That does not make the number fictional. Extrapolation of this kind is one of the most powerful and legitimate tools in observational science. The same basic logic used to estimate populations of everything from fish in an ocean to trees in a forest too vast to walk end to end. But it does mean the number carried a kind of built-in uncertainty from the moment it was calculated, an uncertainty that rarely survived the trip from a scientific paper into a headline or a textbook sidebar. Within a few more years, as ground-based and early space-based surveys continued refining their methods, published estimates would settle into a range closer to 100 to 200 billion, a figure that would itself come to dominate textbooks and museum placards for much of the following 2 decades. That uncertainty would not stay hidden for long, because the Hubble Deep Field, remarkable as it was, still had limits of its own. Faint galaxies it likely missed, distances it could not fully resolve, structure it could not yet see. And less than a decade later, astronomers would return to a similar strategy, with a longer exposure and a more sensitive instrument, to ask a harder version of the same question. Not whether the patch of sky was truly empty, they already knew it was not, but whether even 3,000 galaxies in that grain of sand sliver had been enough to see everything actually there. There is a particular kind of moment in science where a number stops behaving like a measurement and starts behaving like a fact of nature, settling into public consciousness with a permanence the original researchers never intended for it. That is roughly what happened in the years following the Deep Field's release. The immediate figure to emerge from the 1996 press coverage was 50 billion galaxies, a careful, defensible revision of the previous lower estimate. But as the number moved through television specials, encyclopedia entries, and subsequent ground and space-based surveys, refining the count further over the following years, it settled, by the end of the decade, into a rounder, more widely repeated figure, closer to 100 billion, a number that would go on to anchor public understanding for most of the following 2 decades. The image itself became something close to a cultural artifact, reprinted in newspapers worldwide, displayed in planetariums, reproduced on classroom posters beside images of nebulae and planets. It carried a particular emotional charge that few astronomical images before it had managed, because unlike a photograph of a single planet or a single galaxy, however beautiful, the deep field showed density. It showed depth. Every point of light in that grain of sand patch was not a star, but an entire separate galaxy, and something about seeing that fact laid out visually, rather than simply stated as a number in a paper, seemed to land differently in the public imagination than any purely verbal description could have managed. Within the scientific community itself, the image proved just as productive. In the years following its release, the small patch of sky it captured became the subject of nearly 400 separate research papers, an extraordinary output for a single 10-day observation of what had been chosen, deliberately, for looking like nothing at all. Journalists covering the release, understandably, needed a number to anchor their reporting, something more graspable than a technical description of extrapolation methods and statistical uncertainty. Whatever figure was in circulation at a given moment, 50 billion in the immediate aftermath, closer to 100 billion within a few years, became that anchor. It appeared in television specials. It appeared in encyclopedia entries. Within a handful of years, it had achieved something close to the status of an established constant, spoken with the same casual confidence normally reserved for the number of planets in the solar system or the speed of light. This is worth sitting with, because it reveals something true about the relationship between science and public understanding that has nothing to do with anyone acting in bad faith. Scientists working on the deep field data understood perfectly well that their number carried real uncertainty, that it depended on assumptions about uniformity and detection limits that might not hold up under closer scrutiny, that it represented a snapshot from one particular instrument at one particular moment in the development of observational astronomy. Papers describing the result included careful caveats, confidence intervals, discussion of systematic errors. Almost none of that survived the journey into public consciousness. What survived was a number, stripped of its uncertainty, because uncertainty does not fit comfortably into a headline or a museum placard. To put this in human terms, imagine a scientist taking a single, careful measurement of a coastline using the best instrument available and being fully aware that a more precise instrument might reveal considerably more coastline hidden in inlets and small bays too fine to detect with current tools. The scientist reports the measurement honestly, along with that caveat, and the caveat simply does not travel as far as the number does. Within a generation, the number stands alone, treated as final, even though the person who originally measured it never claimed anything of the sort. This pattern would repeat again with the number that eventually replaced the 100 billion figure, and it would repeat once more after that, because the actual practice of astronomy is not a search for a single final total that, once found, closes the question permanently. It is a slow, ongoing process of refinement, where each new instrument reveals a version of the universe slightly more complete and slightly more surprising than the one that came before it. The number the public had settled on by the end of the 1990s felt final. It was never intended to be. And within less than a decade, better instruments would begin quietly, methodically, proving that it was not. By the early 2000s, Hubble had been in orbit for over a decade, and the technology carried aboard it had continued to improve, even as the telescope itself remained the same aging structure launched in 1990. In 2002, astronauts installed a new instrument called the Advanced Camera for Surveys, considerably more sensitive to faint light than the camera used for the original 1995 Deep Field, capable of detecting objects roughly 10 times fainter than its predecessor could manage. With this improved instrument in place, astronomers proposed a natural next step: return to a similar strategy that had produced the original Deep Field, but push the exposure time even further, and use the newer, more sensitive camera to see deeper into the same general patch of apparent emptiness. The decision echoed Williams's gamble nearly a decade earlier in a specific way. Stephen Beckwith, the Institute's director at the time, used his own allocation of director's discretionary time to make it happen, committing 400 separate orbits of Hubble's schedule, an amount of observing time large enough that the choice again required a director willing to spend an extraordinary resource on a target chosen mainly for how little it seemed to contain. Between September of 2003 and January of 2004, Hubble was aimed at a region within the constellation Fornax, gathering 800 separate exposures across nearly 1 million seconds of cumulative exposure time, roughly 11.5 days spread across almost 4 months of intermittent observation. The result became known as the Hubble Ultra Deep Field. What it revealed was not a confirmation of the earlier count, but a meaningful expansion of it. The Ultra Deep Field detected roughly 10,000 galaxies within a patch of sky, only slightly larger than the one the original Deep Field had examined less than a decade earlier, more than 3 times the number found in 1995. This was not because galaxies had appeared where none previously existed. It was because the improved instrument could finally detect galaxies that had been present the entire time, but too faint, too distant, or too redshifted for the earlier camera to register. In simple terms, the extra galaxies the ultra-deep field found were mostly not brighter, closer galaxies that had somehow been overlooked. They were fainter, more distant galaxies, some of them among the most ancient objects ever directly observed, their light having traveled for over 13 billion years to reach the telescope's mirror. Among the faintest and reddest objects captured, roughly 100 galaxies appeared to date, back to a period when the universe itself was only about 800 million years old, barely 6% of its current age. The improved sensitivity was not just revealing more galaxies in an absolute sense. It was revealing an entire additional layer of depth to the universe, populated by galaxies so young and so far away that their light had left them when the cosmos itself was still, in a very real sense, an infant. Extrapolating this new, denser count across the full sky, using the same basic logic applied to the original deep field, pushed the estimated total number of galaxies in the observable universe upward into a range closer to 170 billion to 200 billion, roughly double the widely cited figure from less than a decade earlier. For context, this meant that an estimate treated as close to settled fact throughout the late 1990s had been, by the most careful measurement available, roughly half of what a slightly better instrument would go on to reveal. This is where the softening valve matters most, because a number changing by a factor of 2 can sound, on its surface, like the earlier scientists had simply gotten it wrong. They had not. Every earlier estimate had been an honest, careful measurement of exactly what the available instrument could detect. What changed was not the honesty of the measurement, it was the boundary of what could be measured at all. Each improvement in instrument sensitivity did not correct an error. It removed a limitation, revealing galaxies that had always been there, waiting in darkness too faint for the previous generation of technology to notice. And even the ultra-deep field, remarkable as it was, still carried the same fundamental caveat as every deep field before it. It could only count what it could detect. Somewhere below its detection threshold, fainter still, dimmer still, more distant still, an unknown population of galaxies almost certainly remained invisible, waiting for whatever instrument came next. The question was no longer simply how many galaxies existed within reach of the best available telescope. It had become something more difficult. How many galaxies existed that no telescope, however advanced, could ever directly detect at all? That question, about galaxies too faint for any telescope to directly detect, turns out to have a concrete, well-studied example sitting remarkably close to home. Long before astronomers worried about galaxies billions of light-years away, they had already discovered that even the galaxies nearest to our own, the ones close enough to study in exhaustive detail, kept turning up unexpected faint companions the longer anyone looked. The Milky Way and Andromeda, together with roughly 100 smaller galaxies, form what astronomers call the local group, a modest cluster of galaxies bound together by mutual gravity, extending across a region of space roughly 10 million light-years wide. Most of the mass and light in the local group belongs to just 2 galaxies, the Milky Way and Andromeda, both large spiral galaxies containing hundreds of billions of stars each. But surrounding these 2 giants is a swarm of much smaller companions called dwarf galaxies, and the more carefully astronomers have searched for them, the more of them they have found. Consider how recently many of these companions were actually discovered. The Sagittarius dwarf spheroidal galaxy, a small galaxy currently being torn apart by the Milky Way's gravity, close enough that some of its stars have already been absorbed into our own galaxy's outer halo, was not discovered until 1994. It sits almost directly on the opposite side of the galactic center from Earth, hidden behind an enormous amount of gas, dust, and the sheer density of stars along that line of sight. A galaxy containing what is estimated to be several 100 million stars remained completely unknown to astronomy until the final decade of the 20th century, simply because it happened to sit behind an inconvenient amount of cosmic clutter. Since then, dedicated sky surveys using increasingly sensitive instruments have continued to find more. The Sloan Digital Sky Survey, beginning its observations in the early 2000s, discovered more than a dozen previously unknown dwarf galaxies orbiting the Milky Way within just its first several years of operation, many of them containing as few as a few thousand stars, spread across a volume of space large enough that their overall density of light is barely brighter than the background sky itself. These are sometimes called ultra-faint dwarf galaxies, and they represent, in a very real sense, the detection limit of modern astronomy made visible. This search connects to a genuine, long-standing puzzle in cosmology, one astronomers call the missing satellites problem. For decades, computer simulations based on the standard model of dark matter consistently predicted that a galaxy the size of the Milky Way should have hundreds of smaller satellite galaxies in orbit around it. Yet by the early 2000s, only a small handful had actually been observed. Either the simulations were fundamentally wrong about how galaxies form, or an enormous population of real, physical dwarf galaxies was sitting nearby, undetected, simply because they were too faint for existing instruments to register. As sky surveys grew more sensitive through the 2000s and 2010s, the known count slowly climbed, first into the dozens, and by 2020 to roughly 60 confirmed satellites within about 1.5 million light-years of the Milky Way. Then, in 2024, astronomers using Japan's Subaru telescope reported a survey result striking enough to reverse the entire framing of the problem. Extrapolating their findings across the full sky suggested the Milky Way likely hosts closer to 500 satellite galaxies in total, a number so much higher than anything the missing satellites problem had anticipated that one of the researchers involved described the result, without much exaggeration, as having solved the problem too well. To put this in human terms, imagine trying to count the islands in an ocean using a series of increasingly powerful telescopes mounted on a distant shore. Each improvement in your equipment does not simply confirm the islands you had already counted. It reveals smaller islands you had missed entirely, some barely breaking the surface of the water, easy to overlook even when you know roughly where to look. The local group, close enough to study in exhaustive detail, close enough that individual stars within these dwarf galaxies can sometimes be resolved and counted directly, still continues to yield newly discovered companions well into the 21st century, with each new survey suggesting the true total sits considerably higher than the one before it believed. This local problem has enormous implications for the much larger question of counting galaxies across the entire observable universe. If dwarf galaxies orbiting our own cosmic neighborhood, close enough to study in exquisite detail, were still being newly discovered as recently as the past 2 decades, then the deep field surveys examining galaxies billions of light-years away, far too distant and far too faint for any individual star to be resolved, are almost certainly missing an entire population of small, dim galaxies that current instruments simply cannot detect at that distance. Astronomers do not need to guess that this population exists. The local group demonstrates it directly, close enough to study, still incompletely counted. The open question is not whether distant dwarf galaxies exist in similarly vast, undetected numbers. It is how astronomers might statistically account for a population they know is there but cannot directly see. That statistical challenge, accounting for a population that almost certainly exists but cannot be directly observed, is precisely what a team of astronomers led by Christopher Consolis at the University of Nottingham set out to address in a study published in 2016. Rather than relying primarily on direct detection, the way the original deep field and ultra-deep field surveys had, Consolis's team took a different mathematical approach, one built around something called the galaxy luminosity function. The luminosity function is, at its core, a way of describing how the number of galaxies in a given region relates to their brightness. Bright, massive galaxies are relatively rare. Fainter, smaller galaxies are far more common, and the relationship between brightness and abundance follows a pattern that can be measured accurately for galaxies bright enough to detect directly, then extended mathematically into the fainter range where direct detection becomes impossible. It is, in essence, a way of using the well-measured, brighter end of the population to make a careful, evidence-based estimate about the fainter end that current instruments cannot fully see. Consolis's team combined deep field observations spanning 13 billion years of cosmic history with three-dimensional modeling of galaxy distribution, effectively building a statistical picture of how the total number and density of galaxies has changed over the entire observable history of the universe. Their model accounted for something the earlier deep field surveys had not fully incorporated. Galaxies were not just harder to detect the farther away they sat. They were also, on average, smaller and fainter earlier in cosmic history, in the younger universe, before billions of years of gradual merging combined smaller galaxies into the larger structures more common today. The result of this combined approach was a striking revision, where the ultra-deep field's direct count extrapolation had suggested somewhere in the range of 170 to 200 billion galaxies. Consolis's statistical model, accounting for the undetected faint population the luminosity function predicted must exist, arrived at an estimate of approximately 2 trillion galaxies within the observable universe. Not double the earlier figure, not even 5 times larger, roughly 10 times the number that had, only a few years earlier, been considered a well-established, carefully measured update to the original deep field's count. In simple terms, what Consolis's study suggested was this. For every galaxy bright enough for Hubble to directly photograph and count, there were, statistically, roughly 9 additional galaxies, too faint, too small, or too distant for even the most sensitive instrument available at the time to detect individually. The vast majority of galaxies in the observable universe, according to this model, had never been seen by anyone, not directly, not as an individual point of light on a photographic plate. Their existence was inferred, carefully and rigorously, from the mathematical pattern established by the galaxies that could be seen. Consolis himself, describing the scale of what remained unstudied, put it directly, "It boggles the mind," he said, "that over 90% of the galaxies in the universe have yet to be studied at all." There was an unexpected bonus tucked inside this result, one that connected the new estimate to a puzzle astronomers had been quietly turning over since the early 1800s. Known as Olber's paradox, the question asks something deceptively simple. If the universe contains an enormous, perhaps unlimited number of stars and galaxies, why is the night sky dark rather than uniformly bright, filled edge to edge with overlapping starlight in every direction you look? Consolis's census offered a piece of the answer. with a genuinely vast number of galaxies packed into the universe, the reason the sky still appears mostly dark is not a shortage of light sources. It is that most of that light has never had time to reach us, some of it stretched by cosmic expansion into wavelengths the human eye cannot register at all, some of it still crossing the immense distances involved, and some of it originating from galaxies whose light will never arrive here, a point this video will return to later. This number, 2 trillion, spread quickly through popular science coverage in 2016, in many ways repeating the same pattern that had occurred with the earlier figures 2 decades before it. It appeared in headlines, in television segments, in casual conversation, often stripped of the careful statistical reasoning that had produced it, treated instead as a new, more accurate final answer to the same old question. And in a narrow sense, it was more accurate, built from a more sophisticated model, incorporating more data than any previous estimate. But the number carried an important distinction from the deep field counts that came before it, one easy to lose in translation, and worth sitting with carefully before treating 2 trillion as anything close to a settled fact. The distinction is this. When the original Hubble Deep Field reported approximately 3,000 galaxies within its small patch of sky, that number represented something astronomers could point to directly. 3,000 individual objects, each one visible in the image itself, each one counted by an astronomer looking at actual data. The extrapolation came afterward, when that directly observed density was projected mathematically across the full sky. But the core number, 3,000, was a direct observation. The 2 trillion figure from Consolise's study works differently, and the difference matters more than it might initially seem to. The vast majority of those 2 trillion galaxies were never individually observed by anyone. They are not sitting, uncounted but visible, somewhere in an unexamined photograph. They are a statistical inference, a mathematically rigorous prediction of how many faint, undetectable galaxies must exist, based on the well-established pattern connecting galaxy brightness to galaxy abundance among the galaxies that can be directly seen. To put this in human terms, imagine standing at the edge of a forest at dusk, able to clearly count several hundred trees, close enough for you to see distinctly. Based on decades of careful forestry research, you know that for every large, visible tree in a forest like this one, there are statistically several dozen smaller saplings hidden beneath the canopy, too small and too obscured by shadow and undergrowth to count individually from where you stand. Using that established ratio, you could calculate a total tree count for the forest that might be remarkably accurate, even though you have never actually seen most of the trees you are counting. That calculated number is not fictional, it is not a guess, but it is a fundamentally different kind of number than counting the visible trees directly in front of you. This does not mean the 2 trillion estimate is wrong, or that the astronomers who produced it were doing anything other than careful, legitimate science. Statistical inference of this kind, extending a well-measured pattern into a range where direct measurement is currently impossible, is one of the most productive tools available in observational astronomy, used constantly across nearly every subfield of the discipline. Consider a much closer example, sitting within our own solar system rather than billions of light-years away. Astronomers estimate that the asteroid belt between Mars and Jupiter contains somewhere between 1 and 2 million individual asteroids, larger than a kilometer across. Only a small fraction of that population, roughly 250,000 objects, has actually been individually observed, tracked, and catalogued. The remainder is inferred the same way the faint galaxies are, by measuring the size and brightness distribution of the asteroids astronomers can see clearly, then extending that well-established pattern into the range too small or too dim for current surveys to resolve one by one. No one considers the larger asteroid figure fictional simply because most of those million-plus objects have never been individually photographed. The method is sound, the reasoning is careful, the uncertainty is honestly reported in the original scientific paper, even when it fails to survive into a headline. What it does mean is that the number 2 trillion answers a subtly different question than the one most people assume it answers when they hear it. It does not mean 2 trillion galaxies have been found, confirmed, or directly observed. It means that based on the best available model of how galaxy brightness relates to galaxy abundance, approximately 2 trillion galaxies most likely exist within the observable universe, the overwhelming majority of them currently and perhaps permanently beyond the direct detection capability of any instrument built so far. This distinction is not a criticism of the number. It is closer to the honest, careful shape of the number itself, the part that tends to get smoothed away by the time a figure this large reaches a headline or a documentary narration. 2 trillion is not a count. It is a considered, evidence-based prediction built on real data, subject to real uncertainty, and entirely capable of being revised again, upward or downward, the moment a new instrument or a better model comes along. The asteroid estimate has been revised more than once over the past few decades as better surveys came online, each revision simply narrowing the uncertainty rather than overturning the underlying method. There is no reason to expect the galaxy estimate to behave any differently, and as it turned out, it would not take very long at all before a new instrument arrived capable of testing it. Before moving further into how that revision eventually arrived, it is worth sitting for a moment with the number itself, because 2 trillion is one of those figures the human mind cannot actually hold in any meaningful way, no matter how the comparison is framed. Consider the most common comparison used to try to make it feel real. If you tried to count to 2 trillion, one number at a time, at a steady pace of roughly one number every second, without ever stopping to sleep, eat, or rest, the counting would take you approximately 63,000 years, longer than the entire span of recorded human history, many times over. Longer than the time separating us from the earliest known cave paintings in Europe. An unbroken, uninterrupted act of counting, stretching across a span of time longer than agriculture, longer than cities, longer than written language itself, and even then, you would only just be finishing. Try a different comparison, and the number does not become more graspable so much as it becomes differently ungraspable. 2 trillion is roughly 250 times the current human population of Earth. It sits reasonably close to the most careful modern count of every tree on the planet, a 2015 study led by ecologist Thomas Crowther that combined satellite imagery with hundreds of thousands of ground measurements to arrive at a figure of roughly 3 trillion trees worldwide, a result that came as a genuine surprise even to the researchers who calculated it. Crowther himself admitted as much afterward, saying that if you ask most people to estimate, even within an order of magnitude, how many trees exist on Earth, they simply do not know where to begin, and that he had not expected the answer to land in the trillions either. The number of galaxies in the observable universe, in other words, sits in roughly the same neighborhood as the number of trees standing on the entire surface of this one planet. A comparison that does not make either figure feel smaller, so much as it confirms that both were already beyond intuitive reach before the comparison was made. It is a meaningfully larger number than the estimated number of stars in our own galaxy, which itself contains somewhere in the range of 100 to 400 billion stars, a number already well beyond anything a human mind evolved to track herds, seasons, and kinship groups was ever built to process intuitively. What this reveals is not a flaw in the comparisons themselves, but something more fundamental about the limits of human cognition when it meets numbers at this scale. The human brain, across its long evolutionary history, developed excellent intuitive tools for tracking small, countable quantities, the kind that mattered for survival. A handful of berries, a family group, a herd of animals visible on a horizon. Somewhere well before reaching even a few thousand, that intuitive tracking ability breaks down entirely, replaced by abstract mathematical reasoning that can manipulate enormous numbers symbolically without ever actually representing them as a felt, internal sense of quantity. This is why no comparison, however carefully chosen, ever quite closes the gap between a number like 2 trillion and genuine human comprehension. Grains of sand, trees, seconds, stars. None of these comparisons make the number smaller or more familiar. They simply substitute one incomprehensibly large quantity for another, moving the difficulty sideways rather than resolving it. The mind can understand, abstractly, intellectually, that 2 trillion is larger than 100 billion, larger by roughly a factor of 20. It can perform that comparison as pure arithmetic, but it cannot feel the difference between those two quantities in any meaningful, intuitive way, any more than it can feel the difference between 1,000 light years and 1,000,000. Perhaps the only honest thing to say about a number this size is that its purpose was never to be felt. It exists to be reasoned about, calculated with, compared against other equally vast numbers, refined and revised as better instruments and better models become available. Even the tree count itself was revised sharply upward from a prior estimate of roughly 400 billion, an increase of nearly 8-fold once better methods became available, a small, human-scale echo of exactly the kind of revision this galaxy count has already undergone more than once. And in the years following its publication, that is precisely what began happening to the 2 trillion figure, not because anyone had made an error, but because an entirely new kind of telescope was about to look somewhere no previous instrument had ever been able to see clearly at all. It might help, at this point, to step back from the numbers themselves for a moment, because something about sitting inside a question this large can start to feel less like learning a fact and more like standing at the edge of something. You are, right now, wherever you happen to be listening to this, occupying an extraordinarily specific position within a structure almost too large to meaningfully describe. Not a privileged position, not a central one, simply a particular point on a particular small planet orbiting a fairly ordinary star, roughly 2/3 of the way out from the center of a galaxy that itself stretches somewhere close to 100,000 light years from one edge to the other. Light, moving at its fixed, unimprovable speed, would need 100,000 years just to cross the disk of the single galaxy you happen to live inside, and that galaxy is one among perhaps a few 100 billion stars scattered through it, itself one among some unknown number in the hundreds of billions, or perhaps trillions, scattered through a volume of space so large that light, the fastest thing that exists, has not yet finished crossing it since the universe began. There is a particular kind of vertigo that comes with sitting inside. That fact honestly, rather than skimming past it as a piece of trivia. It is not the vertigo of danger, the way standing at the edge of a physical cliff might feel. It is quieter than that, and stranger. It is the vertigo of scale itself, the recognition that the number being discussed, whether it settles eventually at 100 billion, 2 trillion, or something else entirely, was never really the point of asking the question in the first place. The number was always a way of trying to locate yourself, to understand roughly where you stand within something that has no edges you can walk toward and touch. This is, in a sense, what all of the counting has actually been circling around, since Kant first speculated about island universes in 1755, since Hubble measured the distance to Andromeda in 1923, since a director's gamble in 1995 revealed a grain of sand patch of sky was actually full. Every refinement to the number was also, quietly, a refinement to humanity's understanding of its own position. Not the center of anything, not even a particularly typical example of anything, sitting instead somewhere within an almost incomprehensibly vast and still only partially mapped structure. The Earth is not at the center of the solar system. The Sun is not at the center of the galaxy. The galaxy is not at the center of the universe, because the universe, as far as anyone has been able to measure, does not appear to have a center at all, at least not one that any observer anywhere within it could ever locate or stand at. None of this makes the number less worth pursuing, or less scientifically important. Precise measurement matters, and the difference between 100 billion and 2 trillion reflects genuine, hard-won knowledge about how galaxies form, how they cluster, how the early universe differed from the one visible today. But there is a difference between knowing a number and understanding what the number is actually describing, and the second one, the understanding, tends to arrive more slowly, more quietly, usually somewhere well after the headline has already faded. You exist, at this exact moment, inside a structure large enough that its most careful, most rigorous scientific estimate still carries an uncertainty measured not in percentages, but in entire orders of magnitude. That is not a failure of science. It is closer to an honest description of what it actually means to be small, situated somewhere inside something whose true boundaries have not yet been found and may never be. It is worth being precise about what that smallness does and does not mean. It does not mean insignificant in any sense that should trouble you. It simply means situated, the way a single grain of sand is situated on a beach that no one has ever walked end to end, real and specific, and entirely itself, without needing to be the largest thing present in order to matter to the hand that happens to be holding it. And just as this thought had begun to settle, a new telescope arrived in orbit, one built specifically to look further back into the universe's early history than any instrument before it, carrying the very real possibility of revising the picture once again. The James Webb Space Telescope launched on December 25, 2021, from French Guiana aboard a European Ariane 5 rocket, following a design and construction process that had stretched across more than 2 decades and considerably exceeded its original budget, delays and cost overruns that had, at various points, threatened the mission's survival entirely. It was built as a successor to Hubble, though describing it that way understates a fundamental difference in what the two telescopes were actually designed to see. Where Hubble's primary mirror measures roughly 8 feet across, Webb's measures nearly 22 feet, assembled from 18 hexagonal segments, each one coated in a layer of gold only a few hundred atoms thick, chosen specifically because gold reflects infrared light more efficiently than almost any other material available. The mirror was too large to launch in a single rigid piece, so it was folded, origami style, to fit inside the rocket's 5-meter payload compartment, then unfolded automatically once in space, a sequence of more than 300 individual mechanisms that all had to function correctly, with no possibility of a repair mission if any single one of them failed. Hubble observes primarily in visible and near-infrared light, the same general range of wavelengths the human eye can detect, extended somewhat further toward the red end of the spectrum. James Webb was built to observe almost entirely in infrared, a choice driven by a specific piece of physics tied directly to the question this video has been circling from the beginning. As the universe expands, light traveling across it stretches along with the space it moves through, shifting toward longer, redder wavelengths, a phenomenon astronomers call redshift. The most distant galaxies, the ones whose light has traveled the longest to reach us, are stretched so severely that much of their light, originally emitted as visible or even ultraviolet light, arrives at Earth shifted entirely into the infrared range, invisible to an instrument built primarily to see visible light. In simple terms, Hubble could see distant galaxies, but there was a fundamental limit to how far back it could look, not because its mirror was too small or its camera insufficiently sensitive, but because the light from the earliest galaxies had been stretched beyond the range its instruments were built to detect at all. James Webb, built specifically to observe in infrared, could see past that limit entirely, reaching back toward galaxies that existed within the first few 100 million years after the Big Bang, a period of cosmic history that had remained essentially invisible to every previous telescope. Following its launch, James Webb spent several months traveling to its operational position, a point in space roughly 1 million miles from Earth, known as the second Lagrange point, where the combined gravity of the Earth and Sun allows a spacecraft to maintain a stable position relative to both, without burning fuel constantly just to stay in place. It began science operations in the summer of 2022, and one of its first major research programs involved exactly the kind of deep field survey that had produced the original Hubble Deep Field decades earlier, except now aimed at wavelengths Hubble had never been able to fully access. What astronomers expected, based on existing models of galaxy formation, was a gradual, orderly picture. Early galaxies, according to the prevailing understanding at the time, should have been small, faint, and relatively rare, gradually growing larger and more numerous over the following billions of years as smaller structures merged and matter continued to collapse under gravity. This expectation was built on decades of careful modeling, consistent with everything Hubble had previously observed at the somewhat less extreme distances it was capable of reaching. What James Webb actually found, within its very first year of operation, did not match that expectation. Not by a small margin, and not in a single isolated case that might have been dismissed as an unusual outlier. Distant, early universe galaxies began appearing in James Webb's images that were considerably larger, brighter, and more structurally developed than the prevailing models had predicted should exist at such an early point in cosmic history. And the deeper astronomers looked, the more of these unexpectedly advanced early galaxies they continued to find, each new observing run adding to a pattern that was becoming harder to explain away as noise, instrument error, or an unlucky sample. By early 2023, this pattern had become impossible to dismiss as a fluke of small numbers or observational error. Astronomers had identified multiple candidate galaxies dating to roughly 300 to 500 million years after the Big Bang, a period so early in cosmic history that, according to the standard model of galaxy formation, there simply should not have been enough time for structures of this size and mass to have assembled. In the press coverage that followed, some of these objects earned an informal nickname among astronomers and science writers alike: impossible early galaxies, a phrase that captured, more bluntly than any peer-reviewed paper would, just how uncomfortably the new data sat against existing theory. One study, led by astronomer Mike Boylan-Colchin at the University of Texas at Austin and published in 2023, examined 6 of these unusually massive early candidates and found that several of them appeared to contain stellar masses exceeding 10 billion times the mass of our Sun, at a point in cosmic history less than 500 million years removed from the beginning of the universe itself. One candidate appeared, based on early estimates, to be more massive than the Milky Way is today, despite our own galaxy having had over 13 billion years to grow, merge, and accumulate mass, compared to the few 100 million years available to this newly observed, extremely distant object. Consider what this actually requires, in physical terms, to explain honestly. Boylan-Colchin's analysis noted that for galaxies of this size to form so quickly, they would need to convert almost the entirety of their available gas directly into stars, an efficiency far beyond anything observed in galaxy formation processes closer to the present day, where astronomers typically find that only a modest fraction, often cited around 10%, of a galaxy's available gas actually ends up forming stars over a comparable span of time. If the standard model of galaxy formation and the mass estimates for these early candidates were both correct, something about the process of early star formation would need to be considerably more efficient than anything currently observed or fully understood. This tension does not mean the fundamental framework of cosmology is broken, and responsible astronomers working on this problem have been consistently careful to say so. Rachel Somerville, an astrophysicist studying galaxy formation at the Flatiron Institute, described the period following these early results as genuinely exciting for the field, precisely because it represented real, substantive evidence against a settled prediction, the kind of disagreement between observation and model that drives meaningful scientific progress, rather than merely confirming what was already assumed. To put this in human terms, imagine a carefully constructed model predicting how quickly a city could realistically grow, based on decades of data from similar cities elsewhere. Then imagine discovering a city that appears to have reached a size the model says should have taken centuries to build, in a fraction of that time. The reasonable response is not to assume the city does not actually exist, or that measurements of its size must be wrong. It is to ask what the existing model failed to account for. Perhaps building techniques were more efficient than assumed. Perhaps population estimates elsewhere had been systematically too conservative. Perhaps the growth process itself worked differently under conditions the model had never been tested against. This is essentially where research into these early, unexpectedly massive galaxies stood by 2024 and into 2025, an active, ongoing area of investigation rather than a settled conclusion in either direction. Some follow-up studies suggested that certain of these extremely bright early candidates might not be ordinary star-forming galaxies at all, but active galactic nuclei, the intensely bright regions surrounding supermassive black holes, actively consuming surrounding matter, which can appear far more luminous than their actual stellar mass would suggest, potentially explaining away some, though likely not all, of the apparent tension with existing models. Other researchers found that revised models incorporating bursty, episodic star formation, brief intense periods of star creation, followed by quieter stretches, could account for a meaningful portion of the unexpectedly bright early galaxies without requiring any fundamental change to the underlying physics. What remains genuinely unresolved, as of the most recent research available, is how much of this early universe abundance problem will ultimately be explained by refined models and improved classification of these ambiguous objects, and how much may point toward a real, more fundamental gap in the current understanding of how the earliest structures in the universe actually formed. Whatever the eventual resolution of that specific debate turns out to be, it carries a direct consequence for the question this video has been following from its opening moments. Every estimate of the total number of galaxies in the observable universe, from the earliest ground-based figures through the 2 trillion statistical projection, was built using models of galaxy formation calibrated primarily against galaxies observed at more moderate distances, closer to the present day, where the physics involved was already reasonably well understood and tested. If the earliest period of galaxy formation genuinely worked differently than those models assumed, whether through unexpectedly efficient star formation, misclassified active galactic nuclei, bursty rather than steady star formation, or some combination of factors not yet fully identified, then any total galaxy count built on the assumption that early universe galaxy formation followed familiar, well-understood patterns inherits that same uncertainty. The 2 trillion figure was never claimed to be beyond revision. It was, from the moment it was published, an estimate built on the best available model of its time, openly stated as such in the original research. James Webb's early findings represent exactly the kind of new information that such a model would need to incorporate, one way or another, to remain accurate. This is, in a strange way, precisely how rigorous science is supposed to function, even though it can feel unsettling to encounter as an outside observer, expecting a clean, final answer. A model gets built from the best data available. It makes predictions. New instruments test those predictions against reality. Sometimes reality matches closely, and confidence in the model grows. Sometimes reality diverges, sometimes sharply, and the divergence itself becomes valuable information, a signal pointing toward exactly where current understanding needs revision. Consider how many times, over just the span of this video, that exact pattern has already repeated. Shapley and Curtis, debating in 1920, both reasoning carefully from incomplete evidence, both partially right and partially wrong, resolved only once a genuinely new kind of measurement became possible. The original deep field's 50 billion galaxies, revised upward by the ultra-deep field's more sensitive camera. That figure revised again, by a factor of roughly 10, once Consolise's team incorporated statistical modeling of the undetected faint population. And now James Webb, revealing an early universe that appears more developed, more structured, and more populated than any previous model anticipated, opening the strong possibility of yet another revision still to come. 4 separate instruments, spanning a full century, each one certain in its moment, each one eventually superseded. None of these revisions represent failures of the scientists involved. Each one represents exactly what careful science looks like when it encounters the genuine limits of its own instruments, and then, gradually, patiently, pushes past them. The number has never actually been wrong, in the sense of representing careless or dishonest work. It has simply never been finished, because finishing would require an instrument capable of detecting every galaxy that exists, at every distance, at every level of faintness, a capability no telescope humanity has ever built, or is likely to build in the foreseeable future, actually possesses. Even now, NASA's next major observatory, the Nancy Grace Roman Space Telescope, named for the astronomer often credited as the driving force behind Hubble's original creation, sits close to launch, carrying a field of view roughly 100 times wider than Hubble's, built specifically to survey vast stretches of sky far faster than either Hubble or James Webb ever could. Whatever total this video eventually settles on will likely be revised again once its own survey data begins arriving, simply because that is the shape this search has always taken, one instrument at a time, one honest, temporary answer after another. This raises a deeper question, one that moves beyond simply asking whether current instruments are good enough yet. Even setting aside every uncertainty introduced by detection limits, faint dwarf galaxies, and unresolved early universe formation physics, there remains a separate, more fundamental limit built directly into the structure of the universe itself, one that no future improvement in telescope technology, not even an instrument as capable as Roman promises to be, could ever fully overcome. A boundary made not of distance, but of something considerably stranger, time itself. To understand this deeper limit, it helps to be precise about what the phrase observable universe actually means, because it is easy to imagine it describing some fixed physical boundary out in space, a wall or edge that telescopes simply have not yet reached. That is not what it describes at all. The universe, according to the most well-supported current evidence, began approximately 13.8 billion years ago in an event cosmologists call the Big Bang. Light travels at a fixed, finite speed, roughly 186,000 miles per second, extraordinarily fast by any everyday standard, but not infinite. This means that when you look at any object in the night sky, you are never seeing it as it exists right now, in this present moment. You are seeing light that left that object some time ago and has been traveling toward Earth ever since, arriving only now, carrying an image of the past rather than the present. For nearby objects, this delay is negligible on any human timescale. Light from the sun takes about 8 minutes to reach Earth. Light from the nearest star beyond our own solar system takes over 4 years. But for the most distant galaxies detectable by an instrument like James Webb, the delay stretches to nearly the full age of the universe itself. Light that left its source when the cosmos was only a few 100 million years old, still traveling, only now completing its journey to a mirror built specifically to catch it. This creates a genuinely strange and important boundary, one defined not by distance in the way a horizon at sea is defined by distance, but by time. Since the universe has only existed for approximately 13.8 billion years, there has simply not been enough time for light from anything farther away than that to have reached Earth yet, regardless of how sensitive or powerful a future telescope might become. It does not matter how large a mirror is built, or how sophisticated its detectors are. If light from a particular region of space has not yet had time to complete its journey here, no instrument, however advanced, can observe it. The observable universe is not a wall in space. It is a boundary carved out of time. Here the story gains one further, genuinely counterintuitive layer. If the universe is 13.8 billion years old, a reasonable guess would place the edge of what we can see exactly 13.8 billion light-years away in every direction. The actual figure is considerably larger, closer to 46 billion light-years. This is not a contradiction, though it looks like one at first. The light reaching us today from the earliest visible galaxies left its source 13.8 billion years ago, when that galaxy sat much closer to where the Milky Way would eventually form. But space itself has continued expanding for the entire duration of that light's journey, carrying the source galaxy's present-day location much farther away than it was at the moment the light departed. The light took 13.8 billion years to arrive. The thing that sent it, however, is no longer 13.8 billion light-years away. It is roughly 46 billion light-years away. Carried outward by the same expansion, this video will look at more closely in a moment. In simple terms, imagine standing in a completely dark room, holding a lantern that has been lit for exactly 1 hour. No matter how good your eyesight is, no matter how much you strain to see further into the darkness, you cannot possibly see anything more than 1 light hour away, simply because light from anything farther has not yet had time to reach you and bounce back to your eyes. Improving your eyesight would not help. The limit has nothing to do with vision, and everything to do with elapsed time. This is why cosmologists are careful to draw a distinction between the observable universe, the portion from which light has had time to reach us since the Big Bang, and the universe as a whole, which may extend, and by most current theoretical models almost certainly does extend, considerably beyond that boundary. Every galaxy count discussed throughout this video, from the earliest ground-based figures through the 2 trillion statistical estimate, through whatever revision James Webb's findings eventually produce, describes only the observable portion. It says nothing definitive about what might exist beyond it, in the vastly larger, entirely unobservable remainder of the universe that no telescope, in any conceivable future, could ever directly examine. And this boundary carries one more layer of strangeness still, because the observable universe is not simply a fixed sphere, quietly waiting to be fully mapped given enough time and sufficiently advanced instruments. It is, in a very real physical sense, actively shrinking, even as astronomers continue improving their ability to see within it. That shrinking has nothing to do with instruments failing or telescopes wearing out. It comes from a property of the universe itself, one of the more genuinely difficult ideas in modern cosmology to hold comfortably in the mind, though it follows directly and rigorously from well-established physics. Space itself is expanding. Not simply that galaxies are moving apart from each other, the way objects might drift apart within a fixed, static space, the way ships might slowly separate on the surface of a calm ocean. The space between galaxies is itself stretching, continuously, everywhere, at every point throughout the universe simultaneously. This distinction matters enormously, because it means galaxies sufficiently far apart can, in a real physical sense, be moving apart faster than the speed of light, without violating anything in Einstein's theory of relativity. Nothing is traveling through space faster than light. Space itself is simply expanding, carrying galaxies along with it, and there is no speed limit imposed on the expansion of space itself. This expansion has been accelerating for the past several billion years, driven by a poorly understood component of the universe that cosmologists call dark energy, a name that essentially serves as a placeholder for something whose effects are measured with reasonable precision, but whose fundamental nature remains one of the largest open questions in physics. Whatever dark energy ultimately turns out to be, its observed effect is unambiguous. The rate at which distant galaxies are receding from us is increasing over time, not staying constant, not slowing down. Cosmologists have a specific name for the distance at which this recession speed exactly equals the speed of light, a boundary called the Hubble sphere, currently estimated to sit somewhere around 14 billion light-years away. Beyond that distance, the space between us and a given galaxy is stretching faster than light can cross it, even though nothing there is physically moving faster than light through the space it occupies locally. It is one of the more genuinely strange consequences of general relativity, the idea that the rule against faster-than-light travel applies to objects moving through space, but not to space itself. Here is where this becomes directly relevant to the question of counting galaxies. Some galaxies currently sit at a distance where the expansion of space between us and them is happening faster than light can cross that same distance. Light emitted from those galaxies today, at this very moment, will never reach Earth. Not in a billion years, not in any span of time however long, because the space it would need to cross is expanding away faster than the light itself can close the gap. These galaxies are not merely difficult to observe, they are permanently, physically beyond any possibility of future observation, regardless of what instruments humanity might eventually build. Consider what this means for even the galaxies we can currently see. A significant portion of the galaxies visible in deep field images today galaxies whose ancient light is only now arriving after billions of years of travel, have already, in the time since that light left them, crossed beyond this boundary. The galaxy itself, as it exists right now in this present moment, sits at a distance from which no future light it emits will ever reach Earth. We are looking at galaxies that, in a very real sense, are already gone from our reach, even though the image of their distant past continues to arrive. To put this in human terms, imagine watching a ship sail away from shore, its lantern light still reaching you across the water. But imagine the water itself is stretching, expanding continuously beneath the ship, carrying it away faster with every passing moment. Eventually, a point arrives where any light the ship's lantern produces, from that moment onward, will never cross the growing distance back to shore. You will continue seeing the ship's older light for a long while afterward, the light already partway through its journey. But new light, emitted after that threshold, is gone permanently, sent toward a shore it will never reach. If this is true even for galaxies currently within the observable universe, sitting inside the very light-based boundary this video has just described, then the deeper implication becomes almost impossible to avoid. If a total, final count of every galaxy in existence were somehow possible today, it would already be growing incomplete by the time it was written down, some fraction of its total, permanently receding beyond any future possibility of confirmation, observation, or count. All of this, the light-based horizon carved by the universe's finite age, the accelerating expansion carrying galaxies permanently beyond reach, still describes only what lies within the observable universe, the portion whose light has had time to arrive. What remains is a question stranger and, in an important sense, more honest than any of the numbers discussed so far. Does the universe extend beyond that boundary at all? And if so, does it contain more galaxies, simply sitting beyond any possibility of ever being seen? Most current cosmological models suggest, on strong theoretical grounds, that it almost certainly does. This is not idle speculation, and it is worth being precise about exactly why cosmologists believe it. The evidence rests substantially on something called the cosmological principle, a foundational assumption, well supported by every large-scale observation made so far, that the universe is broadly uniform on the largest scales, without some special central point or privileged edge. Every detailed measurement of the observable universe, from the distribution of galaxies to the faint afterglow of the Big Bang itself, known as the cosmic microwave background, shows remarkable uniformity in every direction astronomers have examined. That afterglow, radiation left over from roughly 380,000 years after the Big Bang, has been measured to be uniform in temperature across the entire sky to a precision of about 1 part in 100,000, once the small distortion caused by our own galaxy's motion is accounted for. To make that precision tangible, imagine a perfectly round marble, shaped so precisely that its surface deviates from a true sphere by no more than a fraction of the wavelength of visible light. Nature, left to its own devices, essentially never produces anything that's symmetrical by accident. The universe, on its largest observable scales, effectively has. If the observable universe, the portion we can actually see, looks broadly similar no matter which direction a telescope is pointed, with no evidence of approaching any kind of edge, boundary, or unusual thinning of galaxies near the limits of detection, the most natural and best supported conclusion is that the universe likely continues in a broadly similar fashion beyond what light has had time to reach us from. Not necessarily infinite, a separate and still genuinely unresolved question in cosmology, but very likely based on current evidence, considerably larger than the portion currently observable, quite possibly by an enormous factor. This is precisely where honest scientific reasoning has to stop, and it is worth being unusually careful and clear about that stopping point, rather than letting the momentum of the previous conclusion carry the video somewhere the evidence does not actually support. Cosmologists can reason, on strong theoretical grounds, that more universe almost certainly exists beyond the observable horizon. What they cannot do, and what no future instrument will ever allow them to do, is directly observe it, measure it, or count anything within it. Any number attached to that unobservable remainder would not be an estimate built from data, however statistical or indirect. It would be pure extrapolation, layered on top of an already substantial extrapolation, built from an assumption of uniformity that, however well supported within the observable universe, cannot actually be tested against the portion it is being applied to. This is not a failure of imagination, and it is not a limitation that better funding or a more advanced telescope could someday overcome. It is a structural, physical boundary built directly into the relationship between the finite age of the universe and the finite speed of light. No civilization, however advanced its instruments might eventually become, will ever observe past the edge, defined by how long light has had to travel since the beginning of time itself. What this means for the question this entire video has been circling is worth stating plainly, without softening it further than the evidence actually allows. The honest total number of galaxies in the universe as a whole, not merely the observable portion, is very likely unknowable, not because current instruments are insufficiently advanced, but because the universe's own physical structure places that number permanently beyond the reach of any conceivable act of observation or measurement, now or at any point in the future. This is not the kind of unknown that patience or funding eventually resolves. It is closer to a boundary drawn by the geometry of existence itself, one this species happens to have been born inside of. So, after nearly 2 centuries of careful measurement, spanning Kant's early speculation, Hubble's distance calculation, 2 separate Hubble Deep Field surveys, a decade-long statistical revision, and James Webb's ongoing reshaping of the early universe, what is the actual, honest answer to the question this video opened with? It helps, briefly, to retrace the shape of that history, rather than simply its conclusion. A philosopher guessed correctly in 1755, with no way to test his own idea. A measurement in 1923 confirmed that guess and shattered the working model of an entire generation of astronomers in the process. A director's calculated risk in 1995 turned an empty-looking patch of sky into 3,000 galaxies. A statistical model in 2016 multiplied that understanding by a factor of 10, and a telescope launched on Christmas Day of 2021 is, even now, still rewriting what the earliest chapters of that story looked like. The most defensible answer is not a single number, and resisting the urge to provide one is, in a genuine sense, the most scientifically accurate response available. Within the observable universe, the portion whose light has had time to reach Earth since the beginning of the universe roughly 13.8 billion years ago, direct observation using the most sensitive instruments currently available has confirmed the existence of several 100 billion galaxies, objects that have actually been detected, individually, in deep field images and large-scale surveys. Statistical modeling, incorporating the well-established relationship between galaxy brightness and galaxy abundance, suggests the true total within the observable universe likely sits considerably higher, in the range of 1 to 2 trillion, accounting for a vast population of faint, small, or extremely distant galaxies that current instruments cannot individually resolve, but whose existence is predicted with reasonable statistical confidence based on patterns observed among the galaxies that can be directly seen. That statistical estimate itself remains under active revision, as James Webb continues returning evidence that the early universe contained more structure and formed it more quickly than previous models anticipated. A genuinely unresolved tension in current astrophysics that may, once fully understood, push the total estimate higher still, or alternatively, may be explained through refined classification of ambiguous bright objects and more sophisticated models of early star formation, without requiring the total estimate to change dramatically at all. As of the most recent research available, this question remains genuinely open, one of the more active areas of observational cosmology at this exact moment. And beyond the observable universe entirely, in the vastly larger remainder that current theory strongly suggests exists, but that no instrument will ever be capable of directly examining, the honest answer is not a number at all. It is an acknowledgement that this portion of the question sits permanently beyond the reach of measurement, a structural limit built into the physical relationship between the universe's age and the finite speed of light itself, a limit no future generation of astronomers, however capable their instruments become, will ever find a way around. What this means, taken as a whole, is that the question, how many galaxies exist in the universe, does not actually have a single, final, correct answer, waiting to be discovered by some sufficiently advanced future telescope. It has a carefully bounded range, several hundred billion confirmed, 1 to 2 trillion statistically likely, within the observable universe alone, and an acknowledged, permanent unknown extending beyond it. This is not a failure of astronomy after 2 centuries of dedicated effort. It is closer to the opposite. It represents astronomers being rigorously honest about the difference between what has been measured, what can be reasonably inferred, and what simply cannot be known, a distinction that takes considerably more scientific discipline to maintain than simply reporting a single confident number would. A less careful field would have settled on one of its earlier figures and stopped there, content with the tidiness of a fixed answer. This one kept measuring instead, kept admitting what the last instrument had missed, kept building the next telescope specifically to find out how wrong the current picture still was. There is something worth sitting with in that distinction, something that extends beyond astronomy itself. The most honest answer science can offer to a question this large is not a number that closes the subject. It is a carefully reasoned boundary, marking exactly where genuine knowledge ends and where humility about the limits of observation rightfully begins. There is a pattern, if you look back across everything this video has traced so far, that appears again and again, quietly, in nearly every stage of this 2-century search. Someone measures carefully, with the best tools available to them. They arrive at a number, and for a while, that number feels complete, feels like an answer, feels like the kind of thing that could be written into a textbook and left there, undisturbed, for a long time to come. And then, without exception, it isn't left undisturbed. A telescope repair mission happens. A more sensitive camera is installed. A statistical model incorporates a population that had gone unseen. A new instrument, built specifically to look further back than anything before it, arrives in orbit and quietly begins returning images that do not match what anyone expected to find there. Each time, the number that had felt finished turns out to have been a waypoint rather than a destination, a careful, honest description of what was visible at that particular moment in the long history of human instruments looking upward. This pattern is not a story about failure, however many times it repeats. It is closer to the actual shape of what learning looks like, when it is being done honestly, at the very edge of what current tools can reach. 50 billion becomes 100 billion, 100 billion becomes 2 trillion, and 2 trillion, even now, sits under quiet reconsideration, not because anyone did anything wrong, but because the universe, whenever a slightly better instrument is turned toward it, tends to reveal that it was larger, older, and more finished than the previous generation of models expected it to be. There is a kind of peace available in that pattern if you are willing to sit with it rather than resist it. Not knowing the final number is not the same thing as knowing nothing. 2 centuries of careful measurement have not failed to answer this question. They have succeeded in mapping, with increasing precision, exactly the boundary between what can currently be known and what cannot yet be reached. That boundary itself has moved, slowly, deliberately, outward, again and again, and it will likely continue moving outward for as long as human beings continue building instruments and pointing them at the dark. Think of everyone who has stood at the edge of that boundary, across the long stretch of this search. Al-Sufi, sketching a faint cloud by candlelight in the year 964, certain only that it was there, not what it was. Kant, guessing at island universes from his writing desk, with no telescope of his own to test the idea. Leavitt, cataloging photographic plates for a wage far smaller than the discovery she was quietly making deserved. Hubble, marking a single photographic plate with an excited var that would end up rewriting the size of everything. Williams, willing to spend 10 irreplaceable days on a patch of sky that looked, to nearly everyone around him, like nothing at all. Each of them stood at whatever the current edge happened to be in their own lifetime, added what they could see from there, and then handed the question forward, unfinished, to whoever came next. Somewhere in the middle of that ongoing motion is where you are listening from tonight. Not at the beginning of this search, and almost certainly not near its end either. Simply somewhere within it, a brief, particular moment in a project that began with a Persian astronomer sketching a faint cloud by hand in the year 964, and that will likely continue, in some form, long after every telescope currently in operation has gone quiet and been replaced by something better. The number was never really the point, though it took the entire length of this search to say that plainly. The point was always the looking itself, the slow, patient, repeated act of pointing an instrument at darkness, and trusting that darkness was not actually empty, simply unresolved. Every increase in that number, from 50 billion to 2 trillion and whatever comes next, has been evidence of exactly that trust being repaid, again and again, by a universe that kept turning out to hold more than anyone standing at the telescope that year had any way of knowing. Return, for a moment, to that patch of sky from the very beginning, the one no larger than a grain of sand held at arm's length, the one that looked, to every telescope before 1995, like simple, uncomplicated emptiness. Nothing there, nothing worth the time or the light-gathering hours it would have cost to examine closely. A director spent 10 days of an irreplaceable resource on it anyway, because he suspected, without proof, that emptiness itself might be an illusion worth testing. It was never empty, not for one single moment of the 10 billion years its oldest light had already been traveling before that patch was ever photographed. It was full the entire time, layered galaxy behind galaxy behind galaxy, each one holding its own 100 billion stars, its own planets, its own long, slow history of formation and collapse and quiet drift through the dark. The emptiness was never a property of the sky. It was only ever a property of the instrument being used to look at it. A temporary limitation, waiting patiently to be outgrown. This is, perhaps, the truest thing this entire search has revealed, more true than any single number along the way. Every patch of sky that still looks empty tonight, wherever you happen to be, whatever direction you might look if you stepped outside right now, is very likely just as full as that first grain of sand patch turned out to be. Not empty, simply unresolved, waiting, the way Andromeda waited for nearly 1,000 years after Al-Sufi first sketched its faint outline, for an instrument patient enough and sensitive enough to finally reveal what had been there all along. Waiting the way the earliest galaxies waited, invisible to every telescope before James Webb, not because they were shy of being found, but simply because no eye capable of seeing them in their own true light had yet been built. There is something quietly comforting in that thought, if you let it settle rather than rushing past it. The universe does not seem to run out of things to reveal, no matter how carefully it has already been searched. Each generation of astronomers, working with whatever instrument happened to exist in their particular moment in history, found exactly as much as their tools allowed them to find, and no more. And it was never because the universe had been fully mapped. It was only ever because the looking had, for the time being, reached its limit. And every single time, without exception, across 2 centuries of trying, the limit turned out to be temporary, never permanent, never final. Simply the edge of what one particular generation, with one particular set of instruments, happened to be capable of resolving. Somewhere, right now, a mirror is being ground to a tolerance finer than anything used to build the instruments this video has described. Somewhere, a spacecraft not yet launched is being tested in a clean room, its gold-plated segments folded carefully against the day they will finally unfold in the dark above the atmosphere. None of that work will finish the question this video opened with. It will simply move the boundary outward again, the way every instrument before it has, revealing a slightly deeper layer of a sky that was always, in truth, exactly as full as it is now. The dark above you tonight is not a void waiting to be filled. It was never a void at all. It is simply the part of the universe that has not yet been resolved, patient in a way that has nothing to do with waiting, because it was never going anywhere. It was always there, all of it, however many trillion galaxies it eventually turns out to hold, quietly present in the dark, long before anyone built an instrument capable of proving it. Long before there was anyone, anywhere, to wonder whether it was there at all. You are listening to these words from somewhere on a small, spinning planet, circling an ordinary star, inside a galaxy that is itself only one among some number too large to state with real confidence. Hundreds of billions, almost certainly. Perhaps 2 trillion. Perhaps more, somewhere beyond the reach of any telescope that will ever be built. The honest answer, after 2 centuries of careful searching, is still a range rather than a number, and that range is not a disappointment. It is the discovery itself. Think of everyone this search has passed through on its way to you tonight. A Persian astronomer sketching a faint cloud by hand 1,000 years before anyone knew what it was. A philosopher guessing at other universes from a desk he never left. A woman cataloging photographic plates, quietly building the ruler that would measure the whole sky, for a wage that never reflected what she had found. An astronomer marking a single photographic plate with an excited word, not yet knowing he had just moved the edge of the known universe. A director spending 10 irreplaceable days on a patch of sky that looked, to nearly everyone around him like nothing at all. None of them arrived at a final number. All of them moved the boundary outward by exactly as much as their moment in history allowed. Somewhere above you right now, whether or not the sky is visible from where you are lying, there is a patch of darkness no larger than a grain of sand held at arm's length. It looks like nothing. It has always looked like nothing to every set of eyes and every instrument that came before the ones capable of finally seeing through it. And it was never nothing. It was always full, layered, impossibly deep, with galaxies no one had yet found a way to see, waiting the way distant things wait, without impatience, without any sense of time passing at all. That is, in the end, what this search has actually been circling, longer than it first seemed to be. Not a final count, not a number precise enough to close the question and move on to the next one. Something closer to a way of standing inside your own smallness, without it feeling like a diminishment. You are one person on one planet, briefly alive inside a structure that has been quietly, patiently revealing more of itself for as long as anyone has thought to look, and it does not appear to be finished revealing yet. Let the number stay unfinished tonight. Let the dark stay full of things not yet resolved. There is nothing incomplete about a universe still being discovered, only about the instruments still catching up to it, one careful measurement at a time, across centuries that will likely keep stretching long after tonight, long after this particular grain of sand, held at arm's length, has finally, someday, given up everything it was quietly holding. Somewhere out past every galaxy anyone has ever counted, the dark keeps going, not empty, never empty, only waiting, patiently, the way it always has.